Now we're reasoning about complex connectedness.
Hello, everybody. My name is Arthur. I'm a fifth-year PhD student working with Wilensky in the Center for Connected Learning and Computer-Based Modeling at Northwestern. I'm really happy to be here today and present LevelSpace. It's a project that I've been working on. I just looked at my code a couple of days ago, and I started writing the first line of code in February 13th, 2012. So it's been almost 4 years coming. And we're finally now at a place where we have a pretty good piece of software, and we can start really collecting data. So LevelSpace, very briefly, is a NetLogo extension. It allows you to run an arbitrary number of NetLogo models at the same time and have all of these models connect, communicate, react to each other. And in that sense, it's sort of it's a software development project. It's a modeling project, insofar as agent-based modeling is now becoming an epistemology and research tradition in itself. And of course, it's a constructionist project on learning, on thinking, trying to figure out what can we do now that we can have people reason about how things are connected and see, look outside of the models that we've been working on for the last many years. Because of this particular venue, I'm going to focus mostly on the parts about LevelSpace that relate to studying thinking, studying reasoning, and designing learning experiences. This video setting here is the PI on the project. We got funding starting about a year and a half ago for 3 years, and so we're about halfway through it now. And we are now at the point where we can we are designing learning activities and rolling them out, implementing them in classrooms. I'll get back to that later. So yeah, the overview, I already went over that. NetLogo, do people in here know NetLogo? Most people, yeah. We saw the presentation earlier today about turtles, and NetLogo is one of those logo variants that deploy many turtles. In the case of NetLogo, sometimes tens of thousands, hundreds of thousands, of millions of turtles. It's an agent-based modeling language that was developed and released by my advisor, Wilensky, in 1999. A review of social science research using agent-based modeling showed a couple of years ago that it was the most often cited agent-based modeling language, but at the same time it's used in education from middle school all the way up to PhD level courses. And so I feel like we can proudly say that we've established NetLogo as this low threshold, high ceilings language that we're using in a lot of really cool contexts. And it's a computational approach to modeling complex phenomena. We program behavior into these computational representations of things. Then we observe the aggregate level outcomes as they emerge from these interactions. So that's very abstract. I'm just going to give an example. It's one of the canonical examples, the wolf-sheep predation model. We have this model, the little white things are sheep, the black things are wolves. Green is grass and brown is dirt. And we have sheep walk around randomly. They eat grass when they can. They metabolize and they die if they starve to death. Similarly, wolves walk around randomly. If they meet a sheep, they eat the sheep, they metabolize, and if they starve, they die. And both of them reproduce with some probability. And just with those very simple rules, we get fluctuations, population dynamics like this. And I hope it's not too much of a stretch to say that this is pretty similar to what we actually observe in the real world. So even with these very, very simple rules, we're able to produce data that looks like what we're seeing in the real world. Simple rules, complex outcomes. So moving on to this, moving away from the idea of just as a computational representation of some sort of phenomenon, and thinking about them as these objects to think with, external representations that embody different kinds of mechanisms. We've used that in the lab that already established couple of decades ago to study things like physics, chemistry, cell biology, population biology, evolution, electricity, and urban development. So a very large span of domains that have all been modeled and then afterwards used to get between things. I'm just going to go over this model because it'll be, I'll use it in some examples in this presentation. So the Wolf-Sheep predation model we already talked about. This is a model of basically of climate change, of the greenhouse gas effect. We have the little yellow dots are photons coming into the atmosphere. Black things here are CO2 molecules. Down here we have heat stored by Earth, and these yellow photons move through the atmosphere. If they hit a cloud, they bounce back into space. If they hit Earth, there's a probability that they get absorbed by Earth and turned into heat. And then after a while, there's a sort of a chance that they escape Earth as infrared light. Infrared light, infrared energy. If there is CO2, then they can sort of get caught in the CO2 and in that sense help heat up the atmosphere. So that's how this works, and based on these interactions, we can then think about what climate change, why climate change happens, and the role of greenhouse gases in climate change. So models, in other words, are these very particular representations at a very particular level of abstraction and at a very particular level of representations. And so when we build models, we make a bunch of decisions about what to include and what to exclude. The model of the wolves and sheep only have wolves and sheep, and that's it, and grass, but nothing else. And of course, that's not really how things are in the real world, but those are good things, because by isolating these particular things, not only do we get a good space for sort of representing things computationally, but we also can ignore the things around the system and allow learners to just focus on the mechanisms that are important in order to explain some particular phenomenon, sort of the least necessary model. But, of course, when we do that, we also draw cosmological boundaries. We make some implicit claims about what's important, what's not important, and we restrict what's even possible to think about. And when we are talking about learning with these models, of course that's important because we want to encourage exploration of things that might be important to learners, and they might find things important that simply aren't in the model. And so far, it hasn't really been able, we haven't been able to do anything about that, apart from have learners build new models that then include the things that that they think is interesting. And so, inspired by this larger movement inside agent-based modeling, in the field of agent-based model, talking about multi-level agent-based models, we developed LevelSpace. And sort of the most ham-fisted way, here are models with boundaries around them, and then LevelSpace removes them, and we can connect models. And that's basically the idea, that we have this new way of connecting models in NetLogo. So, and basically that's what we want to call it, turtles all the way down, that we can now sort of think of models as turtles. We can treat them as things that interact with each other in the same way as turtles inside them have been interacting. And that brings us to what we see as sort of a fundamental claim about models. You might disagree with it, then we can have a conversation about it. But basically that agents and variables in individual models almost always are simplified models themselves. I can elaborate on that with some of the examples. But that by then treating models as agents, we can connect these phenomena, we can explore connections, and then we can design activities around models that are connected, and allow learners and modelers to construct and think sort of with and within and between different phenomena. So we have two of them where we built a graphical user interface, and then this last run where we did a classroom study. And I'll just quickly go over and sort of show you what we found in that. So the first prototype we built was sort of even before we had LevelSpace as we know it now. So we sort of faked it by just having two models run side by side. And we built a user interface that contained all of the, if you guys remember the widgets, all the little monitors and things you can click on, buttons and the other. So we basically turned them into these drop-down menus. And then by clicking on one and dragging an arrow over to one of the other parts of the other model, we allowed people to sort of graphically show how things in one model was related to things in the other model. We sat down with two teachers, Bryan and I, for about an hour and a half. And then first we went over each of the models individually, like I did with you before, and sort of talked to them about what are the individual mechanisms, making sure that they understood that. And then we asked them a very sort of fundamental question: how are these systems connected? Just open-ended question, just to see what are they even, how would they respond to that? And so Henk, one of the two teachers, said, vegetation, I think, is a key thing if we have climate change. So now we have a different environmental conditions for the producers, so the lowest level in this food web, which may affect how many resources there are at the bottom of the primary producers to support the rest of the population. And if there's less vegetation, it's going to affect the sheep, which is ultimately going to affect the wolves as well. So the things that Henk attended to were specifically vegetation and thinking about how, if we have climate change, vegetation is sort of the key difference, the most important thing in this connected system. Christie said it as, I think you'd have the biggest thing in the ratio of the carbon dioxide by photosynthesis versus cellular respiration. So basically, how much CO2 or how much greenhouse gas is being produced in the system versus how much is being absorbed by the grass. So we have wolves and sheep walking around and burping and farting, and then we have grass or binding the carbon dioxide. And so what we thought was interesting about this, sort of very fundamentally, was that first of all we had two teachers who attended to very different things in this system. And because of the differences in what they attended to, the kinds of questions and the kinds of sort of very informal hypotheses that they had about how these systems would react and connect to each other became very different too. And so for us, it was just very preliminarily showed us that thinking about just opening up the question of here are two models, if you understand them, how do you think they relate to each other, seemed to be a good way of studying how people think and the things that they attend to, and as a productive way of thinking about phenomena as how they're embedded in each other, inside or next to each other. So the next thing that we wanted to do was sort of the idea behind our first prototyping was really find out how do we elicit this kind of thinking? How do we get people to talk about things in productive ways and do it in ways that offer us sort of a window on their thinking while they do that. So this one showed having two models and asking people to connect them would at least be one way to go about it. We also built another GUI for trying to help non-programmers write NetLogo code that would then be interpreted by LevelSpace. Basically what we're seeing here is sort of method signatures with a name and some set of parameters and then the code. And I don't know if either of the GUIs were particularly successful, but what was interesting about this was that rather than this time, well, let me just talk about this study. So we're in a computer clubhouse kind of or after-school activity on the south side of Chicago at a public school. We had 13 girls, around 13, right? Or And we had 4 sessions with them of each 90 minutes. And so what we did this time was we said, just tell us what's missing in it. And we broke them up into 4 groups, 3 groups, and they ended up seeing very different things. I'll show you just one of them, but we had sort of, some people were talking about disasters. Did we give them the Wolf-Sheep Predation model? Did we?
Wolf-Sheep was selected.
Yeah, it was selected.
But it was not the only one selected.
That's right, yeah. But we had a couple of groups selecting the Wolf-Sheep Predation model that I showed you, and one group said seasons are missing, which it is. The other said that disasters are missing. And so what they ended up doing was connecting one of the other models in the NetLogo library, the fire model. And then once in a while, the fire would sort of take the grass from this, create a new representation of the grass, run this fire model, and then remove the grass that was fired, that had burned in the other model. And again, it was sort of, for us, one of those sort of, again, at the surface level and preliminarily, seems to be a good way of thinking about opening up this discussion about how a different system's connected, and how can we use modeling as a way of creating higher fidelity models, but also as a way of studying and eliciting thinking about the connectedness of many different complex phenomena. The last model system that I want to show you is something that Corey and I just finished. We're supposed to end about, I guess, the week before we flew out, but because of holidays and because of professional development days, we ended this unit less than 24 hours before getting on the plane. So unfortunately, we haven't really had time to look at the data yet. But in this unit, we took a totally different approach. So in the other ones, we had participants think about systems in a very open-ended way, and in this, we decided alignment. And what happens in this model, in between these 3 different models, is we can buy cows, we can deforest, we can create more or less pasture for the cows to graze on. We can also add fertilizer, and the more food we produce, the larger a population we get. But the larger a population we get, the more greenhouse gases we get. The more greenhouse gases we get, the more the temperature changes, and as the temperature changes, grass might end up growing back more slowly. And so people could either compensate for that by deforesting, which would, of course, release more greenhouse gases into the atmosphere, change the temperature, or they could use fertilizer, which would pollute the nearby lake, which would turn people in your village sick and make them less likely to reproduce. So we had this pretty complex system. Again, sort of not the entire world, but enough of a system that we could look at how students would reason about, first of all, just the complex systems aspects of it. So how do we maximize food production here? And maximizing food production could be, just this interplay between basically how fast grass grows back as a function of the temperature. But then we asked them afterwards to then connect this village and think about how can they maximize the population. And so at that point, there's sort of many different nested levels of carrying capacities. There's a carrying capacity grass, but the grass carrying capacity depends on the temperature and the fertilizer, and the carrying capacity of people, again, depends on not only the carrying capacity of cows and how much food they're producing, but also on this. And so we sort of gave them this complex system, and we had them iterate over different designs of this and say, tell us how you're going to maximize your food production. Tell us what you'll do, how many cows you're going to get, how much grass, how much fertilizer, and tell us why you think that would work. And then have them iterate over their sort of designs and configurations of this system. We don't really have a sense of the data yet, and we haven't run the actual assessment part of it yet. We will do that next week. So right now, this is sort of where we are. But we ran it with 23 high school seniors as a larger 12-day unit on sustainable food production. And hopefully we'll be able to report something more in depth soon. Oh yeah, this one. To be announced. So our future agenda on the LevelSpace are really driven by these two fundamental questions. What does it mean to think between and across systems, which is sort of what we have been doing mostly today, right? Looking at these systems that coexist alongside each other. What we would really like to do too is to think about systems that sort of live inside each other. So one of them could be in the wolf-sheep predation model. All of the wolves and sheep move around randomly. What if we created brains? What if we gave them intelligence? Then we have sort of one big system, an ecosystem containing these smaller complex systems that themselves may be linked or built up from the bottom up. In our preliminary prototyping studies, to use this idea of studying gaps or connections as ways of eliciting thinking, and to use that to study how people reason about phenomena at different levels and find out how we can better design curriculum activities and assessments of that. So that's what I have.
We got about 6-7 minutes for questions.
Models.
Yeah.
And I feel like the learning that Rich was in creating those models, I know is not low floor. I mean, I think it's very hard to create good models,
Yeah.
but it seems like you're giving them to the people you're working with. So how does that change the learning?
As opposed to if they had built them. What we do with the complex system stuff is that if people understand the underlying mechanisms, each of the underlying mechanisms, and then they can sort of explore how those interactions, both at sort of the individual level of an agent and then at mid-levels of collections of agents, all the way up to the aggregate level. If they understand the individual mechanisms, then they can sort of iterate their way through understanding these complex systems when they play around with the problem. I think that if they have built the models themselves, and if they decide what order they want to put in each of these different mechanisms and it's driven by their own curiosity, I think that would be better. I think that they would be better and more quickly able to understand the system as they're constructing it. And unfortunately, the programming of those models would take too long for what we have.
Yeah, well, just observing, one thing that's hard to convey is that in each of these cases, the students or teachers spent a great deal of time understanding the component models. And the activity was to do another level of modeling using that component model to connect to another. And so there is a level of construction that's happening in taking these independent models and making a system out of them.
So is it construction at the level of existing models to understand nature better, or?
I would say yes. I mean, and certainly that's the assumption in a modeling activity. And so what we tried to do was to make the entry into creating the mechanisms with the GUIs that we built, making the programming the mechanisms easier for the students. And so while they may have not built the individual models from scratch, at least they built the connections between them. You can sort of, once they understand each of the models.
And you do get a strong debugging cycle.
Oh yeah, yes.
Because you say, like the teacher who said that the climate change ran it and saw that the scale was wrong, so they got a huge feedback effect that was stronger than expected. So there was iterative, even the iterative debugging comes through even in a very lab level.
Another thing, Christy, when she talked about how the ratio between cellular aspiration and photosynthesis. Thank you. She thought of it, at least the way we understood it at first, as a rate, right? As sort of a delta of something. And then when she and Hank started talking about it, they then started breaking it down into a mechanism that related to individual agents, as opposed to just being sort of a rate that was calculated based on accurate data from the model. And so there is some unpacking, even just in this connecting models, assuming that the people who are reasoning about the model understands the individual mechanisms.
The other thing to mention is that since this is early design study, our goal in going to the field is to understand that second use LevelSpace in building models from scratch. As we're trying to understand the tools for doing that, we want to get rich linking activity going on, and doing the whole soup to nuts thing would be beyond where the technology is. And
would the system support that if I want to just construct at that high level, I can also go deep and open the system and construct at the small level?
Yeah, so LevelSpace currently allows you to open.
So that second GUI is actually for the users to actually do this programming of the connections.
That's right.
Which is something I found fascinating.
Yeah,
I wanted to make sure I understood.
No, that's exactly right. And so basically what it does is, because NetLogo doesn't yet have, introspection and code completion, we pulled out all of the variables, all of the procedures, and then created drop-down menus of them. And so basically what you can do is you have a drop-down menu that's called turtles, you have one that's called wolves, you have one that's called sheep, and then you can take that as it's sort of a faked flock space programming. We can sort of take that as a value, put it into as an argument to in a procedure in another model, and sort of connect them like that. I think it needs a lot more work to make it easy and understandable, but it does work, and that's it. And the idea is exactly to make it easy to sort of connect them.
Because that's always been a problem in NetLogo, but it's really hard to actually get inside. I mean, to actually do programming in NetLogo for,
that is an advertisement. So actually, it is interesting to me. This is my first conference here, but I've been working with NetLogo for a while. To hear the community's perception that NetLogo is most often used as people opening the models library and playing with it and never getting to it. That's a little different from our experience in seeing NetLogo in use, but it also suggests the sense that it's hard to do would lead you to come to at least visit our workshop.
Well, what I find is it's easy to tinker with the code that somebody else made.
Huh?
Like tinker with the code that somebody else made, like the wolf
Right.
from scratch. It's really difficult.
Let's do it.
But it has nothing to do with NetLogo. It's just that complex systems are really
Complex.
hard to represent. Star logo, NetLogo, whatever. They're
Right.
hard to. I mean, you have to really understand it really deeply to be able to create one. So it's hard to facilitate because I don't think teachers have that understanding. So you do. That's why.
I mean, maybe they didn't, but I did work with Star Logo and complex data systems and directions and all that last year with 6th and 7th graders. And I got like amazing stuff from them, and they really, really enjoyed it. And really, I mean, when I say really understood, like they're 6th and 7th graders, but they understood what was happening between.
Yes, but not every teacher is
Oh,
yeah.
right.
Yeah, that's what it has nothing to do with the tools. It's just that,
Star Logo Boa is visual.
Yes,
This
oh,
is
no,
not-
no, I
this is
realize that.
not.
No, I realize that. I've
Okay.
worked in this one too. That's what, no, the block.
There's another insight to this, and I mean, from the perspective of a biology researcher, I can tell you that more often than less, what you find is that these models do not simulate what is happening in the real world, because they are not as complex as the real biological world. And this is not a bad thing, but on the contrary, a very good thing, because what it will allow you is to try to find what are the missing bits.
Yeah.
And those missing bits are exactly the connecting parts. And you can go up in more complex levels of organization, and you can talk about communities instead of population in biology, or you can go down. You can look at
soil chemistry or
physiological processes or whatever, and then you can build all these connections and try to see if these connections and this complexity improves the similarity with the real world. And if it doesn't, then you can go back and tinker, and of course, you always need to dissect little parts and pieces of reality, because if you try to take the whole thing in,
you get the whole world.
It's way too complex.
And I think that's also, one of the first build a bigger model. Why not put it all in a model? And it's not this. I mean, we use these models because they're useful for a very particular perspective. We just want that perspective. And then once we validated that, we verified it, we can start connecting it to other things that are also small enough that we can actually make sense of it. Because with complex systems, I mean, it's hard enough to pin down causality in just a wolf-sheep basic model. Right? When we played around yesterday, we had this thing. Nobody can. I mean, we've been working with models for many years. We couldn't understand what was going on. Then we had to really slow it down and see what was actually happening. And then when we saw it, it made sense. And so, really being able to.
And the actual fact that it doesn't work is a feedback for the scientists to go and ask the right questions.
And keep out their thinking.
Questions.
Yeah.
Yes.
Yeah.
And see what the scale of the question should be answered in. I mean, different.
Yeah.
So I think it's pretty.
Thank you so much.
All right. All right, maybe we should wait.
Oh,
Yeah.
And we want to understand how that is going to play in the network ecosystem, and how people are already starting to use it as an environment that works in schools.